Hello and welcome. Today, we're going to dive into a really fascinating chemical puzzle. Think of it like a mystery. We're going to figure out what really happens inside a combustion chamber, and we'll do it by using two completely different but really powerful detective tools.
So here's the mystery we need to solve. Picture this. You've got a reactor. You put in 24 pounds of pure carbon and 300 pounds of just, regular air. Then you light it up. The big question is, what exactly comes out the other end? Now, it might sound simple, but the answer actually reveals one of the most fundamental laws of the entire universe. So let's figure this out together. To get to the bottom of this, we're going to treat this whole thing like a detective story. We're going to use two totally different methods, two different ways of thinking to get to the truth. Now, each one will give us a unique angle on the problem. But will they lead us to the same answer? Well, let's find out. Okay, so every good investigation has to start with the facts, right? So let's lay out everything we know about this little combustion mystery of ours. This is our official case file, all the clues we need to get started. All right, here are the numbers. These are the hard facts for our case. We're putting exactly 24 pounds of carbon and 300 pounds of air into our reactor. Do the math, that's 324 pounds of stuff going in. And here's a really important clue. This is a complete combustion. That means everything that can react will react, no half measure. Now, hold on, before we go any further, we gotta talk about a special tool our detectives use. It's called the LB mole. I know, it sounds a little weird, but don't let the name throw you. It's actually super simple. Just think of it like a chemist's dozen. You know how a baker counts eggs by the dozen? Well, chemists and engineers use moles to count these gigantic numbers of molecules. It just makes the math way, way easier. All right, time to bring in our first detective. Now this one's a real traditionalist. They believe in following the recipe to the letter, the known chemical formula for how this all works. We call this method the mole balance. And here it is. This is the recipe. It's so simple, it's actually kind of beautiful, right? You take one atom of carbon, that's the C, and you combine it with one molecule of oxygen, the O2, and what do you get? You get one shiny new molecule of carbon dioxide, the CO2. It's like a perfect, simple, step-by-step instruction manual. So how does our first detective actually use this recipe? Well, they follow four pretty logical steps. First, they convert all our pounds into those handy moles we talked about. Second, they figure out exactly how much carbon and oxygen get used up in the fire. Third, they calculate how much carbon dioxide gets created from that. And finally, they just tally up everything that's left over to get the final answer. And after all that number crunching, here it is, the solution from our first detective. The reactor spits out 2 lb moles of carbon dioxide, a little bit of leftover oxygen, about 0.17 lb moles of it, and 8.18 lb moles of nitrogen. The nitrogen just kind of went along for the ride with the air. So, case closed? Not so fast. It's time to bring in our second detective. Now, our second detective, they have a totally different way of doing things. They couldn't care less about the recipe. This detective is meticulous, maybe a little obsessive, and they live by one simple rule. You cannot cheat the universe. They're just going to count every single atom. This method is called the elemental balance. You see, the idea here is incredibly powerful. It says that no matter what kind of fiery chaos is happening inside that reactor, the number of carbon atoms you put in has to be the exact same number of carbon atoms that come out. Same for oxygen, same for nitrogen. Atoms don't just vanish into thin air, and they don't just appear out of nowhere. All they can do is get rearranged. And this just lays it out perfectly. Take a look at the atoms in column. That's our starting inventory. Now look over at the atoms out column. For carbon, 2N, 2 out. For oxygen, 4.34 in, 4.34 out. The numbers match up perfectly, even though those atoms have all been shuffled around into new molecules. The books are perfectly, and I mean perfectly, balanced. And this right here just drives the point home. If you subtract the atoms out from the atoms in, what's left? What's the difference? It's 0. A big, fat 0. Nothing was lost. Nothing is unaccounted for. Every single atom that went into that thing has been found on the way out. It is a completely flawless accounting job. So we've had two different detectives on the case. They used two very different methods to solve our combustion mystery. We had the recipe follower, and we had the atom counter. Now it's time for the final verdict. And here it is, the moment of truth. It doesn't matter if you follow the recipe or if you count every single atom, you get the exact same answer. Both methods, completely independent of each other, prove what's coming out of that reactor. And that's the key takeaway here. Two totally different paths led us to the exact same truth. That's how you know you've got it right. You know, this whole exercise is really just a demonstration of one of the most fundamental laws in all of science, the law of conservation of mass. It was summed up perfectly by the famous chemist Antoine Lavoisier. Nothing is lost, nothing is created, everything is transformed. In any closed system, matter isn't just made or destroyed, it just changes its shape. Those carbon atoms we started with, they're still there. They're just hanging out with some oxygen atoms now. So we've seen this unbreakable law of balance in chemistry, but it kind of makes you wonder, doesn't it? Think about your own life, whether you're balancing a budget or your time or even what you eat. Where else is this fundamental principle of what goes in must come out an absolute unbreakable law? It's something to think about. Thanks so much for joining me.